Welcome back to the deep dive. Today we are really getting down to the basics, stripping away all those layers of abstraction. We're looking at the absolute bedrock of how our devices talk to each other on a network, the Ethernet Local Area Network, the LAN.
That's right. And specifically, we're diving into the core logic of the LAN switch. I mean, this is the device that quietly sits there handling pretty much every piece of internal traffic in, well, almost every business, university, data center you can think of.
It's kind of the unsung hero, isn't it?
Absolutely. This deep dive is crucial because while people often focus on routers, IP addresses, layer 3 stuff, the actual movement of data packets between local devices, that relies entirely on the layer 2 switch.
Okay.
So if you understand how a switch thinks, how it makes its decisions, you really understand the fundamental choreography of any modern campus or enterprise network.
And it's based on surprisingly simple logic, you said, even though the performance needs are huge.
Exactly. Simple rules, but executed at blinding speed.
Okay, so let's unpack the architecture a bit, because where the switch lives kind of changes its focus, right? We're thinking about a typical modern LAN setup. There are really two main places you find these switches doing their work.
Yeah, broadly speaking, first you've got the campus LAN. This is probably what most people picture. Switches tucked away in wiring closets somewhere.
Right, connecting all the user devices.
Exactly. Desktops, VoIP phones, maybe wireless access points plugging into them. They aggregate potentially thousands of end-user connections.
And the challenge there is scale, and maybe users moving around.
Scale, user mobility, power over Ethernet, security.
Yeah.
Lots going on there.
And then the second big area, this is where the serious data crunching happens, the data center LAN.
Precisely. This is usually a more controlled environment, often a closed room, highly organized. It's where the servers live, the storage arrays, the applications that serve up all that information to the users out on the campus LAN.
So the demands are different there, lower latency maybe.
Definitely. Data center switches are optimized for super low latency, incredibly high bandwidth between servers. Think east-west traffic flow. But here's the key thing. Whether it's a switch serving students in a dorm or handling critical financial transactions in a server farm, their number one job, their absolute primary mission, it's the same.
Okay, what is it?
Forward Ethernet frames to the correct destination MT address and do it instantly at wire speed.
Wire speed, that's the kicker. This isn't software thinking about it.
This is specialized hardware, ASICs, making decisions in microseconds for every single frame.
Okay, so achieving that seemingly simple goal, just send the frame to the right place, requires, you said, 3 distinct things happening all the time.
Yeah, 3 essentially independent actions working in parallel constantly. We can really structure our whole discussion around these 3 functions. They're like the pillars of switching logic.
Right, pillar number 1, the main job.
That's the forward or filter decision. It's the output action. A frame comes in, the switch looks at the destination MSE address and instantly decides. Which board does this need to go out? Or does it need to go out at all?
Okay, forward or filter based on the destination. Pillar 2. This sounds like intelligence gathering.
You could call it that. It's learning. This is more of an overhead function preparing for the future.
Yeah.
It happens as the frame arrives, even before the forwarding decision sometimes. The switch looks at the source MSE address where the frame came from.
Ah, okay.
And it uses that to update its internal map, figuring out, okay, that device lives off this port.
Building its knowledge base. Got it. And the third pillar, the safety net.
Crucial one. Loop prevention. This is the defensive mechanism. Switches have to actively cooperate with each other, usually using something called a spanning tree protocol, or STP.
Why? What's the danger?
Redundancy. Networks need backup paths. But if you just plug cables in to create loops, and then a frame gets sent everywhere, well, it loops forever, instantly crashes the network.
Okay, wow. So STP prevents that disaster.
Prevents the meltdown, yes. It manages those redundant paths.
All right, let's tackle pillar 1 first. The core forward or filter decision. You said it all hinges on the MAC address.
Absolutely. We need to appreciate the Ethernet frame header itself for a second. Layer 2 switching logic lives and dies by 2 fields in that header. The 6-byte source MAC address and the 6-byte destination MAC address.
Right, those hexadecimal numbers you see, like 0200.1111111111. Unique hardware identifiers.
Exactly. And for this core forwarding job, the switch basically ignores everything else in the frame, like the IP address inside. It only cares about that destination MAC.
Okay, but to make that decision fast, it needs some kind of lookup table, right? A map.
Precisely. It maintains a dynamically built table, usually called the MAC address table, sometimes switching table or bridging table.
But you gave us a tech nugget earlier, the hardware name.
The CAM table, content addressable memory.
Okay, CM. Why is that specific type of memory so important here? What does content addressable mean?
It's fundamentally different from regular RAM, random access memory, that your computer uses. With RAM, if you want data, you have to know its address, its location, and tell the chip, go look at location 12324.
Right.
CAM works backwards. You give it the content you're looking for in this case, the destination master address, say 020.222.2222222, and the CAM hardware simultaneously compares that MC against every single entry in its memory, all at once.
Wow, okay. Not searching one by one.
No sequential search. It instantly returns the associated value, which for a switch is the outgoing port number. Bang.
And that's what enables wire speed forwarding, that hardware parallelism.
That's the magic, yes. Milliseconds, microseconds sometimes, between receiving the frame and sending it out the correct port.
Okay, so armed with the super fast CAM table, let's walk through the ideal scenario. Forwarding known unicast frames. Known unicast meaning the destination MC is already in the CAM table. The switch knows where it's going.
Perfect. Let's use the example. Fred wants to send a frame to Barney. Fred's computer sends a frame. It hits switch 1 on, let's say, port S01. The destination MAC in the header is Barney's address, 0200.2222.2222.
Okay, frame arrives. Switch grabs that destination MAC.
Immediately presents 022.2222.2222 to the CAM. The CAM instantly replies, match found, associated port, F02.
So the switch now knows Barney is reachable out port F02.
Right, so it forwards the entire frame, unchanged, only out port F02.
And just as importantly, it doesn't send it out any other ports.
Crucially, yes, it filters it from F01, where it came in, F03, F04, and so on. This containment is fundamental. It keeps traffic localized, prevents unnecessary network chatter. Only Barney gets the frame.
Now, you mentioned something important earlier. In a bigger network with multiple switches, each switch makes its own decision, right? It's not like there's a central brain.
Absolutely critical point. The decisions are independent and local. Imagine Fred is sending to Wilma, and the path goes through SW1, then SW2, then SW3 to reach Wilma. SW1 receives the frame from Fred. Its CAM table says, to get to Wilma's MS, send this out the port connected to SW2. So it does. SW2 receives it. Its local CAM table says, Wilma, she's reachable via the port connected to SW3. Forwards it again, then SW3 gets it, checks its table, finds Wilma's MA is directly connected to, say, port SO5, and sends it out only that port.
So each switch only needs to know the next hop based purely on its own learned information.
Exactly. It doesn't know or care about the full end-to-end path, just its local piece of the puzzle. That's what makes Layer 2 switching so scalable and efficient. Simple, local decisions chained together.
That's elegant, actually. Okay, so that's forwarding. What about the other side of that coin, the filtering rule? When does a switch decide not to forward?
Filtering is basically the switch deciding, nope, this frame doesn't need to go anywhere else from here. It discards the frame.
Why would it do that?
The main reason is efficiency, preventing unnecessary traffic. The specific rule is quite neat. If the switch looks up the destination MAC in its CAM table, and the outgoing port listed in the table is the exact same port the frame just arrived on.
Okay. So if Fred sends to Barney, the frame comes in SO1, the table says Barney is out FO2. It forwards. But if Fred sent a frame to himself, maybe. Or if the destination was somehow also on FO1.
Right, or more commonly, imagine Fred and Barney are plugged into an old-style hub, and that hub is plugged into switch port FO1. Fred sends to Barney, the frame goes into the hub, hits the switch on FO1. The switch learns Fred is on FO1. Now, the hub also blasts the frame to Barney directly. Barney gets it, but the switch also needs to decide what to do. If it looked up Barney and found Barney was also out FO1 because he's on the same hub segment, the filtering rule kicks in.
So the switch says, destination is out the same port it came in on. No need for me to send it back out there, and it drops it.
Precisely. It prevents the switch from sending the frame back onto the segment it just came from. It optimizes things, avoids redundant transmissions. It knows the destination segment already received the frame directly.
Okay, that makes sense. It confirms jobs already done locally.
Yeah.
But all of this forwarding and filtering relies entirely on having good information in that CAM table. If the table's empty, the switch is flying blind. Which brings us nicely to Pillar 2, the learning process. How does the table get built?
This is where the switch's dynamic nature really comes into play. You know, if Network admins had to sit there and manually type in the MSE address for every single computer, phone, printer.
Oh man, nightmare, especially with devices moving all the time, laptops going between desks, offices.
It would be completely unmanageable, so switches learn automatically.
Okay, how simple is the logic behind that learning?
It's beautifully simple. The switch learns by looking at the source MSE address of every single frame that comes into it.
Okay, wait, not the destination like forwarding, but the source, where it came from.
Exactly. That's the crucial difference. Forwarding logic uses the destination. Learning logic uses the source.
Why?
Because the source address tells the switch definitively, the device with this AMBAN address is currently alive and reachable via the port this frame just arrived on. It's direct evidence of location.
So the internal process is just observe and record.
Pretty much 2 steps. 1, a frame arrives on, say, interface FLA. 2, the switch looks at the source MAXE address in the header. Let's say it's 0200.IPLA2, then checks its CAM table. Is 0200.IPLA up to AT? For port up to SABLA. If yes, maybe just update the timestamp. If no, or if the existing entry is for a different port, it adds or updates the entry. MATC 0200.FBUA. And that's it. That's the whole learning process.
That's the core logic. It's an essential overhead function. It happens constantly, passively, just by watching the traffic flowing through it. This builds the map needed for the primary job of forwarding.
Let's visualize it. Start with the switch just powered on, cables plugged in, but the CAM table is completely empty, blank slate. Okay, frame 1. Fred, MAC 020.1111.101 sends his very first frame, Dustin for Barney. MAC 0200.2222.2222. The frame enters the switch on port SR11.
Right. First thing the switch needs to learn, it sees the source MAC 0200.1111.1111 arriving on F01.
Its internal logic kicks in. Device 0200.1111.1111 port F01. It adds the entry to the CAM table. MAC 0200.111111 port F01.
Okay, Fred's location learned. Now what about forwarding that first frame? We'll get to that. But let's assume it gets to Barney somehow. Now frame 2. Barney replies to Fred. Barney's reply frame enters the switch, maybe on port FO2.
The switch sees this incoming frame on FO2. What's the source MAC this time?
It's Barney's MAC 020.2222.2222. Checks the table, doesn't see Barney yet, adds the entry. MAC 020.2222.2222, checks the table, doesn't see Barney yet, adds the entry. MAC 0200.2222.2222, mage port F02.
And just like that, after one exchange, the switch knows where both Fred and Barney are? Exactly. It's this reciprocal nature of most communication. Devices tend to talk back and forth. That conversation automatically populates the CAM table, making future forwarding between them efficient and targeted. The network learns itself.
That's quite clever. But hang on, you raised a really good point there. What if a device doesn't talk back or doesn't initiate traffic? Like, say, I plug in a brand new server that's designed to just passively receive multicast data streams. It never sends anything out itself unless specifically pulled.
Oh, yeah, that's a classic edge case. And you're right. If a device is truly completely silent, never sends a single frame with its own MMAC as the source toent, the switch will never learn its location through this dynamic process.
So traffic sent to that silent server, the switch wouldn't know where to send it.
Not initially, no. The switch would treat frames destined for that server's MS as an unknown unicast, which we need to talk about next. It would end up sledding it.
So for truly passive devices, you might need manual intervention.
You'd have to configure a static MAC address entry in the switch's CAM table. Manually tell the switch, MAC address 0200 CCCCC. CCCC is permanently located off port F02.
Okay, so static entries bypass the dynamic learning. Good to know.
It highlights that the system fundamentally relies on devices actually transmitting something to be learned dynamically.
Right. Okay, let's go back to Fred's very first frame to Barney. The switch learned Fred's location, MAC 020.111111 101111 on F01 from the source address, fine. But when it looked at the destination address, Barney's 0200.2222.2222, the CAM table was still empty for Barney. It hadn't learned his location yet.
Exactly. This is the situation we call an unknown unicast. The destination is a specific device, unicast, but the switch has no entry for it, unknown.
So what does the switch do? It can't just drop it. Fred expects Barney to get the message.
It has no targeted information, so it has to resort to the only option that guarantees delivery.
Flooding.
Flooding, that sounds messy. It is, a bit. It means the switch makes copies of the frame and sends out every single active port in the same broadcast domain, usually the same VLAN.
Except the port the frame originally came in on.
Correct. Must exclude the incoming port, FO1 in Fred's case, to prevent immediately sending it back to the source. So blast the frame out, FO2, FO3, FO4, and so on. It's like shouting into the void, hey, is 020.222.2222 out there somewhere?
Why do this? What's the rationale? Seems inefficient.
Two key reasons. First, guarantee delivery within that broadcast domain. Barney must be connected to one of those other ports so he will receive the frame eventually.
Okay, ensures the message gets through that first time.
Second, and this loops back to learning, it forces a response. When Barney receives that flooded frame, he'll process it. And assuming he needs to reply to Fred.
His reply frame comes back into the switch, maybe on FO2.
And that reply allows the switch to learn Barney's location, MAC 020.22222.2222 on F02, by looking at the source address of the reply.
Ah, so the initial flooding is actually the mechanism that triggers the learning of the unknown destination.
Precisely. Flooding solves the immediate delivery problem and simultaneously solves the information problem for all future frames between Fred and Barney. After that first exchange, their traffic becomes known unicast, efficiently forwarded only between FO1 and FO2.
Okay, so flooding is like a one-time setup cost for initiating communication with an unknown device.
That's a good way to put it. The source materials diagram, figure 5.7, shows this. Well, Fred sends, table's empty for Barney, switch floods it out to Barney, Wilma, Betty. Everyone gets it that first time.
Now, are there other times flooding happens, besides unknown unicasts?
Yes. The other major category is broadcast frames.
Like ARP requests, or DHCP discovers.
Exactly. Frames that are intentionally addressed to everyone on the local network segment. They use the special destination MNC address FFFF, FFFF.
So by definition, these have to go everywhere.
Right. The switch doesn't even need to check its CAM table for FFFF. The rule is simple. If the destination is the broadcast AMC, treat it exactly like an unknown unicast. Flood it out, all ports except the incoming one.
Okay, so unknown unicasts and broadcasts both get flooded.
Correct.
This brings up something you mentioned, the broadcast domain and VLANs. How do VLANs affect this flooding behavior? Because flooding everywhere sounds like it could get out of control on a large network.
And it absolutely would. That's precisely why VLANs, virtual local area networks, are so fundamental. A VLAN is, by its very definition, a layer 2 broadcast domain. Meaning that when a switch needs to flood a frame, either unknown unicast or broadcast, it only floods it out to other ports that are assigned to the same VLAN.
Ah, so if Fred is in VLAN 10, say sales, and the servers are in VLAN 20, data center.
And Fred sends a broadcast, like an ARP request, trying to find a printer in sales. The switch will flood that frame only out to other ports also configured in VLAN 10. It will never cross the boundary into VLAN 20.
So VLANs act like watertight compartments for broadcasts and floods.
Exactly. They contain the necessary evil of flooding to only the relevant segment of the network. This segmentation is absolutely vital for performance and security on any reasonably sized network. It keeps sales chatter out of the data center and vice versa.
Okay, containment is key. But now, we have to talk about the dark side. Flooding is necessary, okay, but networks need to be reliable. We need backup paths, right? Redundant links between switches in case one cable gets cut or a port fails.
Absolutely non-negotiable in any serious network design. You need redundancy for resilience. Multiple paths are good.
Wait, if we have multiple physical paths between switches, maybe a triangle or a square of connections, and then an unknown unicast or a broadcast frame gets flooded.
You have just created the recipe for a layer 2 loop disaster.
This is where pillar 3, loop prevention, becomes critical.
Beyond critical. It's existential for the network. Without an active loop prevention mechanism, adding redundant links would instantly render the network unusable the moment the first broadcast or unknown unicast hits.
How bad is it really? You hear broadcast storm, but maybe people think it just slows things down.
Oh, it's not a slowdown. It's an immediate catastrophic failure. Think denial of service attack, but when you inflict on yourself. I've seen it. Walked into wiring closets where every single port LED on every switch is solid green, flickering maybe slightly because they were processing frames at 100% line rate endlessly.
Wow.
The frame counters go ballistic. The switch CPUs spike to 100% just trying to process the storm, often becoming completely unresponsive to management access. You can't even log in to try and fix it. The network is effectively dead.
Let's use the book's example. 3 switches, A, B, and C, connected in a triangle. Larry, on A, sends a frame to Bob, whose location is unknown.
Right. Switch A gets the frame. Doesn't know Bob's MAC, so what does it do?
It floods, sends copies out the ports going to switch B and switch C.
Okay, now switch B receives a copy from A. Switch B also doesn't know Bob, so it floods the frame.
Out its other ports, including the one going back towards switch C.
And switch C does the same thing. It got a copy from A, floods it out, including sending a copy towards switch B.
Ah, I see the problem. Now switch B gets the copy from C.
And treats it as another new frame to be flooded, because its source was C, not A. And C gets the copy from B and floods that again.
The frames just start circulating faster and faster.
Exponentially. Each flooded frame generates more flooded frames on the next hop. Within milliseconds, all the links between A, B, and C are completely saturated with copies of the same frame chasing each other around the loop. Total network meltdown.
Okay, that's terrifying. So the mandatory solution is the spanning tree protocol, STP.
Yes, or one of its faster modern variants like RSTP or MSTP. But the core idea is the same. STP's entire purpose is to logically disable redundant paths to prevent loops, while still allowing those paths to exist physically for failover.
How does it logically disable a path? Does it shut down ports?
Essentially, yes, STP runs on all the switches, and they talk to each other using special messages called BPDUs, Bridge Protocol Data Units. Through exchanging BPDUs, they perform a little election.
An election? For what?
To choose one switch in the entire Layer 2 network to be the root bridge. Think of it as the captain, the central reference point.
How is the root bridge chosen?
Based on the lowest bridge ID. The bridge ID is a combination of a configurable priority value and the switch's own base MSC address. Lower is better. Usually the switch with the lowest priority wins, or if priorities are tied, the lowest MAC address wins.
Okay, so one switch becomes the root, then what?
Then every other switch in the network figures out its single best lowest cost path to reach that root bridge.
Path cost, based on link speed.
Primarily, yes. Faster links like 10 gig or 1 gig have a lower STP cost than slower 100 meg links. Switches add up the costs along the path, always referring the path with the lowest total cost to the root.
So each non-root switch identifies its best port to reach the root.
Correct. That specific port on the non-root switch is called the root port. It's always in a forwarding state, actively sending and receiving data towards the root.
Okay, what about other ports?
Then, on every network segment, like the cable between two switches, the switches decide which one of them has the better path back to the root bridge from that segment. The port on that switch, the one with the better path, becomes the designated port for that segment. It's also in a forwarding state, responsible for sending traffic onto that segment.
So on any link between two switches, one end is typically designated and the other end might be a root port if it's the best path back.
Could be a root port, or it could be.
Neither.
Right. If a port is not selected as a root port, and it's not selected as a designated port, it means it's part of a redundant, higher-cost path. STP forces that port into a blocking state.
Blocking. And what can a blocking port do or not do?
A port in the blocking state cannot send or receive regular data frames. It can't forward user traffic at all.
Ah, so that's how it breaks the loop, by strategically putting certain ports into this non-forwarding state.
Exactly. It effectively prunes the physical topology down to a logical tree structure, a single active path between any 2 points in the network at any given time. It only listens to BPDUs in the blocking state, just to know if the main path fails.
And if the main path does fail, say the link connected to a root port goes down.
Then STP detects this, because BPDUs stop arriving, recalculates, and potentially transitions one of those previously blocking ports into a forwarding state as a new root port or designated port to restore connectivity using the backup path.
Wow. Okay, that's a crucial safety mechanism. And you said this is all on by default.
Absolutely. Which brings us to how these things behave right out of the box and how we actually manage and verify them.
Right. That ready-to-switch state. It seems amazing that you can often just plug in cables and power up a switch, and it starts working correctly and safely.
It's designed that way.
Yeah.
Key default settings make it plug and play for basic functionality. 1. All the switch interfaces are typically enabled by default. 2. They're all assigned to the default management VLAN, which is usually VLAN 1, so they can all talk to each other initially.
Right. One big broadcast domain to start.
3. Things like speed and duplex negotiation are usually set to auto.
Makes sense.
4. And critically, MAC address learning, enabled. Forwarding filtering logic, enabled. Flooding behavior, enabled. And spanning tree protocol, enabled by default on all VLAN 1 ports.
So it's Instantly smart enough to learn, fast enough to forward, and safe enough not to loop right from power on.
That's the goal, yes. Basic operation without needing manual configuration.
Now, if we want to peek inside the switch's brain, see that CAM table it's building? That's the command.
The fundamental command, at least on Cisco iOS, which is very common, is show MAC address table dynamic.
Show MAC address table dynamic.
Yeah.
And dynamic means the ones it learned automatically.
Correct. As opposed to static entries we might configure manually. This command pulls the current learned entries straight from that CAM, essential for troubleshooting.
Let's break down the output you typically see from that command.
Sure. You'll usually see columns like VLAN, confirms which broadcast domain the address belongs to. Often just one if you haven't configured others.
Okay.
MAD address, the actual 6-byte hardware address that was learned, like Fred 0270.1111.1101
Got it.
type. Usually says dynamic for learned entries, might say static if manually configured, or sometimes other types related to security features.
Dynamic is what we expect from the learning process.
Right. And finally, ports. This tells you which physical interface on the switch this MAC address was last seen coming in on, like FAB01 or G1-20, depending on the interface naming.
So this output is basically the switch's current map. This ME lives in this VLAN. I learned it dynamically, and it's off this port.
Exactly. It's the ground truth according to that switch.
Now, on a busy switch, that command could spew out thousands of lines, right? How do you find what you're looking for?
Yeah, raw output isn't very useful in a large environment. You need filters. Thankfully, the command supports them.
Like if a user calls saying, my desktop can't connect, and you know their machine's MAD address.
Perfect scenario. You don't want to scroll. You use the address filter, show MAC address table dynamic address base, the AMC address here.
And it just shows that one line. Or nothing.
Exactly. Instantly tells you if the switch sees that device, and if so, which port and VLAN it's on right now. If you get no output, the switch hasn't learned that MAC recently. Maybe the cable's unplugged, or the device is off. A huge troubleshooting step.
What if you don't know the MAC, but you know the physical port? Like, what devices are plugged into port S015 on the third floor?
Then you filter by interface. Show MAC address table dynamic interface, put the interface ID here, like file 15.
And that shows all MNACs learned on that specific port.
Correct. Useful for seeing what's connected, or if maybe multiple devices are somehow sharing a port, which could be legitimate or suspicious.
Okay. And maybe filter by VLAN, too, to see all devices in a specific segment.
Yep. Show MAC address table dynamic VLAN number. Great for auditing, making sure only the right kinds of devices are showing up in, say, your secure server VLAN. These filters turn a data fire hose into precise information.
Makes sense. Okay, so the table gets built dynamically. Does it just grow forever, or do entries get removed?
They definitely get removed. The CAM memory is finite, but more importantly, networks change, devices move, you need a cleanup mechanism. This is managed by the aging time.
Aging time? Sounds like entries have an expiry date.
Pretty much. Every time the switch learns or refreshes a dynamic max entry because it saw a frame from that source, it starts a timer for that specific entry. The default aging time on most switches is 300 seconds, 5 minutes.
So the clock starts ticking.
Right. If the switch sees another frame from that same source MAC address on that same port before the 300 seconds are up, it resets the timer for that entry back to 0.
Ah, use it or lose it, basically. As long as the device keeps talking, its entry stays fresh.
Exactly. But if that device goes completely silent, sends absolutely no frames for the full 300 seconds the timer expires, and the switch automatically removes that dynamic entry from the CAM table, poof, gone.
Why is that necessary? Why not just keep them? Seems like relearning might take a moment.
2 main reasons. First, memory management, especially on older switches or in very large environments, keeps the table from filling with stale entries. But the much more important reason is accuracy and mobility.
How so?
Imagine Fred takes his laptop, unplugs from port F01 in his office, walks down the hall to a meeting room, plugs into port F024.
Okay.
If the switch kept the old entry, Fred Massive 01 forever, when someone else tries to send something to Fred after he's moved, the switch would incorrectly forward it to the empty F01 port. Traffic would be black holed.
Ah, right.
But with the aging timer, after 5 minutes of silence from Fred on F01, that entry disappears. When Fred plugs into F024 and sends his first frame, maybe DHCP or ARP, the switch learns his new location, Fred Massive 024, instantly and correctly. The aging mechanism cleans up the old, incorrect information.
Okay, so aging handles stale entries due to inactivity or moves. What about the table just getting full? You said CAM is finite, maybe 8,000 entries or something on a decent switch.
Right. It's possible, especially in environments with lots of transient devices or maybe even during certain types of network attacks, MAC flooding attacks.
So if the table is full and a new device connects and sends a frame, what happens? Does the new device just not get learned?
No, the switch has a policy for this. It needs to make room. It will remove the oldest dynamic entry currently in the table, the one that hasn't had its timer reset for the longest time, even if that entry hasn't actually hit the full 300-second aging time yet.
So it sacrifices the least recently used entry to make space for the brand new one.
Correct. It prioritizes learning newly active devices over potentially stale older ones when memory is constrained. The assumption is the oldest one is the most likely to be gone anyway.
Got it. And can administrators manually clear out entries if needed?
Yes. There's a clear MAC address table dynamic command.
Like a forced refresh.
Exactly. You might use it during major network changes, troubleshooting weird connectivity issues, or maybe after clearing up a security incident.
Can you clear specific entries or is it all or nothing?
Usually have options. You can clear the entire dynamic table globally, or you can be more surgical. Clear only for a specific VLAN, or only entries learned on a particular interface, or even clear just a single specific MAC address entry. Much less disruptive than wiping the whole thing if you know what you're targeting.
Okay, that makes sense. So we have dynamic learning, aging, and manual clearing managing the table. Let's just circle back one last time to that idea of switch independence. It seems really important.
It is fundamental to how Layer 2 scales. Remember the example. Fred is on SW1's port S01. SW1 connects to SW2 via, say, port G02 on both switches.
Right.
SW1's CAM table learns. Fred's MC MASH S01. Fred is local. But SW2 also learns about Fred when Fred sends traffic through SW1 to reach somewhere else. SW2 sees Fred's source MC arriving on its G02, the link from SW1. So SW2's CAM table learns Fred's MC value 02.
So SW1 thinks Fred is directly connected. SW2 thinks Fred is reachable via the uplink to SW1. They have different views based on their position.
Completely different, but both correct from their local perspective. Neither switch knows or needs to know the entire network map. They just maintain their own local CAM table, reflecting where sources were last seen relative to them.
And that distributed local knowledge is enough to get the frame where it needs to go, hop by hop.
Exactly. It avoids the need for complex synchronization or a central map, which would never scale to the size and speed of modern LANs. Local decisions, global connectivity.
All right. So to recap the core logic we've unpacked today, 3 pillars. 1, forwarding or filtering, based on the destination MAC address, using that super fast CAN table lookup. Send it out the one right port or drop it.
Check. The primary job.
2, dynamic learning, building that CAM table by watching the source MA address of every incoming frame. Constant passive intelligence gathering.
Check. The overhead function that enables the primary job.
3, STP loop prevention, the essential safety net. Cooperating with other switches to find the best path and logically block redundant paths to prevent catastrophic loops caused by flooding.
Check. The critical defense mechanism.
These 3 things, running constantly and independently, really define how a modern switch operates.
That's the essence of it, yes. Simple logic, complex interactions, incredible speed.
Okay, fantastic. So let's leave our listeners with a final provocative thought to, well, chew on. Something that connects these pieces. We talked a lot about the CAM table aging time, that use it or lose it policy, default 300 seconds, keeping the table fresh, and handling device moves.
Right, the 5-minute timer.
And we talked about STP, the safety net, blocking redundant links, but being ready to unblock them instantly if the primary path fails. For resilience.
Yeah, the failover capability.
Okay, put those together. Imagine a critical link fails. STP does its job beautifully, unblocks the backup path instantly. Traffic can now flow over the new path.
Okay, network connectivity is restored logically.
Think about the CAM tables on the switches. They just spent potentially the last 5 minutes learning all the MSC addresses via the old, now failed path.
Ah, so the entries in the table are still pointing towards the ports connected to that dead link.
Exactly. Those entries haven't aged out yet. The 300-second timer might still have minutes left to run for many of them.
So, if new traffic arrives destined for one of those MACs immediately after the failover, the switch might still try to forward it out the port associated with the old, failed path based on the stale CAM entry.
For up to 300 seconds, potentially. Creating a temporary black hole until either the entry finally ages out or the destination device happens to send some traffic back over the new path, forcing a quicker relearn.
That's a really interesting point. the disconnect between STP's potentially immediate logical failover and the CAM table's slower timer-based convergence.
So the question for you is, what's the real-world impact of that potential mismatch? How significant is that few seconds or potentially minutes of misdirected traffic after a topology change? And how do modern high-availability network designs actively mitigate that? Do they just tune the aging timer way down? Or are there faster mechanisms to flush stale entries when STP makes a change?
That delves into the nuances of rapid convergence protocols, maybe event-triggered MJOS flushes.
Yeah, bridging that gap between layer 2 resilience and layer 2 learning speed is a constant challenge in network design. A really great question to explore further.
Definitely something to think about. Thanks for joining us for this deep dive into the fascinating logic of the humble LAN switch. We'll see you next time.